right? So in this lecture, we'll explore something called direct sum decomposition, which is essentially a way of decomposing a vector space as a sum of different subspaces. We'll see what sum of subspaces mean, and we'll see how projection matrices come into the picture, how they can help us in expressing these subspaces. And overall, the goal of this exercise will be to prove what is called the primary decomposition theorem. So what do I mean by a sum of subspaces? So suppose that we have a vector space W. I suppose that we have vector subspaces V1, V2 up to script weak A. These are subspaces of some vector space script V. Then the set of all sums of vectors from each of these VI's is what I call the sum of the subspaces. So if V1, V2 up to Vk are vector subspaces, then the set of all x1 plus x2 plus x3 all the way up to xk, where each xi comes from script Vi, is called, it also forms a vector space. That's easy to see, and this is what I call the sum of these subspaces. Okay. So for example, if I take the xy plane, right, the xy plane as V1, and maybe the z-axis as V2, then the sum of these two subspaces would be R3, right? Because every vector in R3 can be written as a sum of a vector from the xy plane and a vector along the z-axis. Similarly, I can also write this as, right, I can also construct, so I can take the xy plane and I can take the xz plane as V2, then the sum of these two subspaces is also equal to R3, right? So there's something different about these two subspaces. So both of them sum to R3, but there's something distinctively different about the two examples that I just gave. The example is the following, and the difference is the following. So in one case the subspaces are independent, and in the other case they are not. So given a collection of subspaces of a vector space, I'll say that they're independent if I take vectors x1, x2 up to xk, where each xi comes from Vi. So if x1 plus x2 plus x3 plus so on up to xk equal to 0, then this can happen only if each xi equal to 0. So each xi comes from script Vi, and the only way that xi's can sum to 0 is if each xi is equal to the 0 vector. Okay. So, and moreover, if v1, v2 up to vk are independent subspaces, then the sum of these subspaces is given a special name. It's called a direct sum of these subspaces, and it has this special notation. So v1 plus v2 plus all the way up to vk. So in LaTeX, this would be the /o plus operator, right? So this is v1 o plus, v2 o plus, v3 all the way up to vk. All right. So again, let's revisit the examples that we had. So on the one hand, let's take v1 to be the xy plane, right, and v2 to be the z-axis, right? So if I take any x1 from v1 and x2 or v2, then it's obvious that x1 plus x2 can be equal to 0 only if x1 and x2 are both equal to 0, because if I take the xy plane and something along the z-axis, no matter how I choose two vectors, I cannot make it 0 unless they are both equal to the 0 vector, and this is basically just follows from linear independence, right? Now on the other hand, if I take v1 to be equal to the xy plane and v2 to be equal to, say, the xz plane, then there is a way I can choose x1 and x2 such that x1 plus x2 equal to 0, but x1 and x2 are both not equal to 0. So for example, I can choose, since v1 has to be in the xy plane, I can choose alpha 0 0 to be x1, right? This obviously lies in the xy plane, and x2 to be equal to minus alpha 0 0. Clearly this lies in the xz plane, so but x1 plus x2 is equal to 0. Okay, so, and moreover, so therefore if I call, right, so if I call this, so this is v1 and this is v2, then R3 is equal to the direct sum of v1 and v2. R3 is also equal to, let me call this v1 prime and v2 prime, then R3 is equal to the sum of v1 and v2, but it's not the direct sum. Alright, so now let's suppose that so we have a collection of subspaces of v1, v2 up to vk, and let us call w to be equal to v1 plus v2 plus so on up to vk. There's no other assumptions, just that they're just arbitrary subspaces of v. Then it turns out that the following three statements are equivalent. The first statement is that the vi's are all independent. Okay, so that's statement number one. Statement number two says that the intersection of vi with v1 plus v2 all the way up to vi minus 1, this gives just the 0 vector. Okay, and the third statement is that if I take an ordered basis for v1, let's call it b1, an ordered basis for v2, let's call it b2, and so on all the way up to bk. So each bi has a certain number of vectors which is equal to the dimension of vi. Then the collection b1, b2, and so on up to bk. So if I take all these basis vectors put together form this set, then this set forms a basis for w, where this is how I define w, right? So, and these are if and only if statements. So if these vectors are independent, then these vectors form a basis for w, and similarly if each bi is a basis for vi, and if this collection forms a basis for w, then all the vi's are independent, and if v1 through vk are independent, then this property is satisfied, and if this property is satisfied, then v1 through vk are independent. Okay, so maybe let's just see this in the context of the two examples that we had. So for example, if v1 is equal to the xy plane and v2 is equal to the xz plane, then let's see, is this property satisfied? v1 intersection v2, sorry, v2 intersection v1, it is not equal to the 0 vector because the intersection is equal to the x-axis, right? Okay, so is property 3 satisfied? It is not, because if you look at, let's say, the x-axis, the y-axis, so this is a basis for v1, and the x-axis and the z-axis forms a basis for V2. But then if I take them together, so if I take them as a not as a set but as a sequence, then this is not a basis, because this vector and this vector are linearly dependent. So it forms a spanning set for W, but it is not a basis. All right. So I won't prove all of these statements, but maybe prove a part of it, and I'll let you try to work out the rest on your own. Okay. So let's try to prove that statement 1 is equivalent to statement 2. So V1, V2 up to Vk are independent if and only if Vi intersection V1 plus V2 all the way up to Vi minus 1 is equal to the 0 vector. Now to prove this, it helps to prove the contrapositive. So what do I mean by that? So if V1 through Vk are not independent, then this does not happen, right? So that's the contrapositive. And another contrapositive is that if this is not satisfied, then V1 through Vk cannot be independent, right? And both of them are pretty obvious if you think about it. So now suppose that V1 in Vi intersection, suppose that statement 2 is not satisfied. Okay, so which means that there exists some I such that Vi intersection V1 plus V2 and so on all the way up to Vi minus 1. So this is not equal to the 0 vector. So there exists some non-zero vector in this intersection. Let us call this alpha, right? So alpha, this vector alpha belongs to Vi, and it also belongs to this sum, right? Since it belongs to the sum, I can write alpha as alpha 1 plus alpha 2 so on up to alpha I minus 1, right, where each alpha I belongs to Vi, right? Okay, so now since the vector alpha belongs to Vi and Vi is a vector space, minus alpha should also belong to Vi, right? And therefore minus alpha plus alpha 1 plus alpha 2 on up to alpha I minus 1 equal to the 0 vector. And obviously alpha is non-zero, so you have a non-zero linear combination, a non-zero sum giving you the 0 vector, and therefore the Vi's cannot be independent, right? So the Vi's must be dependent. So now let's prove the other way around. So if V1 through Vk are not independent, then this cannot happen, right? So since they are not independent, so if these subspaces are not independent, then there must exist some vectors alpha 1, alpha 2, so on, alpha k, such that so not all of these are 0, such that alpha 1, so the sum for I, alpha I is equal to the 0 vector, right? So let us suppose that say j is the largest number between 1 and k, such that alpha j is not equal to 0. Okay, so alpha j plus 1, alpha j plus 2 and so on all the way up to alpha k are equal to 0 in this particular collection, right? So since alpha j is not equal to 0, you can write alpha j so plus some I going from 1 through j minus 1 of alpha I, this is equal to 0, or minus alpha j is equal to sum I going from 1 through j minus 1 alpha I minus 1. So the left hand side is an element from Vj, whereas the right hand side is an element from V1 plus V2 so on, all the way up to Vj minus 1, right? So therefore you've just proved that if Vi's are not independent, then the property 2 is not satisfied. Right? So if property 1 is not satisfied, then property 2 is not satisfied. If property 2 is not satisfied, then property 1 is satisfied. Therefore these two properties are equivalent. Okay, and similarly you can prove that property 1 and property 3 are equivalent using a similar fashion, and this implies that all the three properties are equivalent. Alright, so now that we've seen what sums of subspaces are, let us try to represent them in terms of linear transformations. And the way we do this is using projections. So recall the definition of a projection matrix or a projection operator. So an n by n matrix A is a projection matrix if A squared is equal to A. Right? So let's see some examples. So here is one simple example, 0, 0, 1, 1. Right? So you should see that if you square this particular matrix, then this is equal to the matrix itself. But I also want you to pause this video and think about what this particular projection matrix represents. So geometrically, what is this doing to any point in the xy plane? Right? So think about what this is projecting onto. Right? Similarly, you can take the following example, 0, 0, say 2, 1. Right? So this is also another projection matrix, and right, so this is also another projection matrix, and this. So I also want you to pause the video and think about what this particular projection matrix represents geometrically. Right? So all of these are projections onto a particular line, and the goal is to just identify which line this is. Right? So note that you've seen so most of the projections that you might have encountered so far were orthogonal projections, right? Especially in the context of least squares. Right? But these are not orthogonal projections. For example, this is not an orthogonal projection, right? Here is another projection. So this is a 3 by 3 matrix. Once again, what does this projection represent? Right, so this projection represents so this matrix represents projection onto the xy plane, right? All right. So you've also seen projections in a challenging problem previously. So recall the problem where you are given a plane passing through the origin, right? So this was the problem of finding the shadow of a particular object onto a plane or a sheet of paper. So you have an infinite sheet of paper, which is basically a plane passing through the origin, and you are given a particular direction vector. Maybe this is the direction vector, right? So in this particular example, you were so basically what you had to do was, given an object which is a collection of points, you had to compute the shadow, which was essentially the projection of this particular set onto the xy plane. Oh, sorry, onto this particular plane, right? And in this, it's it's useful to think about the null space and the column space of the matrix, which represents this particular projection. Now you would have noticed that the column space of this particular projection matrix is basically this plane, right? So this plane gives you the column space because that is the range of the projection matrix. But what is the null space? Right? So think about what the null space is. So if this were the direction, this is the origin. So if this particular vector represents the direction in which the light is shined, then the subspace spanned by this vector, or the line passing through this vector, this gives the null space, right? Because if you have any point which is along this line, since the light is passing through the along this direction and through the origin, so any point along this line gets mapped by the projection matrix to the zero vector. Right? Okay. So now let's see some properties of projection matrices. Right. So suppose that calligraphic R and calligraphic N represent the range. So let calligraphic R represent the range of a projection matrix A, and calligraphic N represent the null space of the projection matrix A. Okay, so we'll prove some properties about A, R, and N. Right. So firstly, any vector V lies in the range if and only if A times V is equal to V. Right. And that is, it's fairly obvious, because if so it can lie in the range, if V is in the range of A, then V can be written as A times X for some vector X in Rn, and if you look at A times V, then this is equal to A square times X, which is equal to A times X. Right. All right. So it helps to think about this in terms of the four fundamental subspaces. So this is your domain Rn. This is your codomain Rn. You have these four subspaces: the row space, the null space, right? So the null space is the orthogonal complement of the row space. Any vector in Rn can be written as a sum of a vector from the row space and a vector from the null space. And we know that the row space, every vector in the row space is mapped to a non-zero vector. Every non-zero vector in the row space is mapped to a non-zero vector in the column space. And every vector in the null space is mapped to the zero vector. Right, so this is the zero vector. Okay. So every vector in the row space is mapped to a non-zero vector in the column space, right? And therefore you can write Rn, right? Rn, which is the entire vector space. So in this case, the range and the null space turn out to be independent of each other, because if you take any vector, any non-zero vector in R and any non-zero vector in N, then they can never sum to the zero vector, right? Because if you take any X from XR from the range and take any vector, So you take any xr and xn, and suppose that xr and xn are both non-zero, then a times xr plus a times xn is equal to a times xr, right? And since xr is in the range of a, this is equal to xr, right, which is non-zero, right? So the spaces R and N are independent, and you can also see that R and N, the sum of R and N gives you the entire vector space. Another very interesting property is that let's suppose that we're given two subspaces R and N, where R represents the range of a particular transformation and N represents the null space of that particular linear transformation, and let's suppose that they satisfy this property that Rn is equal to calligraphic R plus calligraphic N, the range plus, so Rn is equal to the direct sum of calligraphic R and calligraphic N. Then, and if the linear transformation is a projection matrix, then it is unique. So in other words, you cannot have two different projection matrices which have the same range and the null space, right? So note that this is special because this does not necessarily hold for an arbitrary linear transformation. So if there is no constraint on the matrix to be a projection matrix, then you can have two different matrices having the same range and the null space. So for example, let's take the projection onto the xy plane, right? So for this particular matrix, the range is equal to the xy plane, and the null space is equal to the z-axis, right? Now let's look at the following linear transformation, right? This also has the same range. The range is equal to the xy axis, and the null space is also equal to the z-axis. However, this second matrix over here is not a projection matrix, and it's easy to verify. Just multiply this matrix with itself, and you won't get back the same matrix, right? But on the other hand, if R and given R and N, if you cannot have two different projection matrices having the same range and null space. The other very interesting property is that every projection matrix is diagonalizable, right? And so here's a question for you. Given that we've seen these three properties, 1, 2, and 3, what can you say about the eigenvalues of the projection matrix? I want you to pause the video and think about this. So for a projection matrix, the eigenvalues can either be 0 or 1, nothing else, right? And why is this true? Because this is true because every vector can be written as a sum of a vector from the range and the null space. So we've seen this, right? We've seen that Rn is equal to the direct sum of the range and the null space, right? And therefore a basis for Rn, so you can take a basis, let's call it u1 up to uk. So let's suppose that, sorry, u1 up to say ul. Suppose that L is the rank of the matrix, the projection matrix A, and let's suppose that u1 u2 up to ul is a basis for the column space, and ul plus 1 up to un is a basis for the null space, right? We know that for every matrix in the range, in the column space, A times ui equal to ui. So this has eigenvalue 1, and for every vector in the null space, A times uj is equal to 0, which is 0 times uj. Right? So the eigenvalues are either 0 or 1. And another way to see this is that if you look at, so we know that a squared is equal to a, right? So in other words, a times a minus I is equal to the 0 matrix. So x times x minus 1 is an annihilating polynomial of a, and it turns out that this is also the minimal polynomial of a. And since the minimal polynomial has distinct roots, the matrix must be diagonalizable, right? Okay. But really, what is the connection between projections that we've just discussed and direct sums of subspaces that we've seen earlier, right? So let's suppose that V, vector space V, can be written as a direct sum of subspaces V1, V2, so on, Vk. So we have this direct sum decomposition of V into subspaces V1, V2 up to Vk, right? So this direct sum decomposition implies that every vector alpha in the subspace, in say Rn, can be uniquely written as alpha 1 plus alpha 2, so on, plus alpha k. So this representation where each alpha I is from Vi, so if we have this direct sum decomposition, then each alpha can be written as alpha 1 plus alpha 2 plus all the way up to alpha k, where this representation, the alpha i's, are unique for a given alpha. So in other words, if you can write alpha as alpha 1 prime plus alpha 2 prime, so on, plus alpha k prime, then it must necessarily imply that alpha 1 equal to alpha 1 prime, alpha 2 equal to alpha 2 prime, so on, alpha k equal to alpha k prime. Now I want you to pause the video and try to prove this yourself, why this cannot be the case. As in, why can't the alpha i's and the alpha I primes be different, right? And the reason why they can't be different is suppose that you had two different representations for a given alpha. So you fix an alpha, and suppose that the alpha i's are different from the alpha k's, right? The alpha I primes, sorry. Now if you look at the difference between the two, so we have alpha equal to the first equation and alpha equal to the second equation. If I take the difference between the two equations, then I get 0 vector equal to alpha 1 minus alpha 1 prime plus alpha 2 minus alpha 2 prime, and so on, right? And if at least for one I, if the alpha I is not equal to alpha I prime, then it means that I have a sum of vectors. So note that each of these come from Vi, right? So I have vectors alpha 1 double prime, alpha 2 double prime, and so on, not all of which are 0, which sum to the 0 vector, right? So the alpha 1 double prime, which is equal to alpha 1 minus alpha 1 prime, alpha 2 double prime is alpha 2 minus alpha 2 prime. The sum of these alpha I double primes, this gives the 0 vector, right? And this is impossible since we know that V is the direct sum of the Vi. So in other words, the V1, V2 up to Vk are independent, and so this cannot happen, right? So as a result, every vector in Rn can be written uniquely as a sum of vectors from each of the VI's, right? And since this is the case, I'll define a transformation EI. So since this transformation is unique, I'll define EI of alpha equal to alpha I, right? So this is a linear transformation, right? So which maps every alpha to the corresponding alpha I, right? So the ith linear transformation maps alpha to the vector alpha I, which is uniquely determined by this representation, right? So this is true. So what properties do these EIs have, right? So firstly, EI square equal to EI, that should be obvious, right? And that is because EI of alpha is equal to EI of alpha I, which is alpha I, because alpha I is in VI, right? So therefore each EI is a projection matrix, right? So the EI defined in this particular fashion is a projection matrix. And what can I say about EJ for j not equal to I? Right? So if I take any vector EI of EJ of alpha, right? So this is EI of alpha j, but since the vectors, the subspaces are independent, this is equal to the zero vector, right? So EI EJ is equal to the zero matrix, right? And what can you say about the sum of the EIs? So E1 plus E2, so on all the way up to EK, right? So if we take any vector alpha and E1 plus E2, so on up to EK of alpha, so this is equal to E1 alpha plus E2 alpha, so on EK alpha, right? But this is alpha 1 plus alpha 2, so on alpha k, right? But this is what? This is just alpha, right? So the sum of all these transformation when operated on alpha gives you back alpha, and this happens for every vector alpha. And what this implies is that E1 plus E2 plus E3 all the way up to EK should give you the identity matrix, right? Okay, so therefore what we've just seen is that if V can be, if any vector space can be written as a direct sum decomposition of V1, V2 up to Vk, then you have projections. Then you can construct these projections E1, E2 up to Ek, where each EI is a projection onto Vi, which satisfies the following properties: EI EJ equal to 0. If you multiply two different E1 and E2 or EI and EJ, then this gives you the zero matrix, and the identity matrix can be decomposed as a sum of E1, E2 all the way up to Ek. And in fact, you can also prove a converse result. That's not too hard to show, that if you can suppose that you have projections E1, E2 up to Ek, any arbitrary projections where each EI is a projection onto some vector space Vi, right? So let Vi be the range of EI, and these projections satisfy the property that EI EJ equal to 0 and the identity matrix is equal to E1 plus E2 all the way up to Ek. So if we have E1, E2 all the way up to Ek, which are matrices such that each EI is a projection and suppose that, let us call Vi to be the range of Ei. And in addition, if these projection matrices satisfy the property that Ei Ej equal to the 0 matrix for all I not equal to j, and the identity matrix is equal to E1 plus E2 so on up to Ek, then it is true that the vector space V or Rn can be written as a direct sum of V1, V2 up to Vk. So note that we only define so these are just properties of the projection matrices, and these in particular imply that their ranges are all independent of each other, and the sum gives you the entire vector space V. Right? So maybe to see a quick example, let us look at a direct sum decomposition of V onto two subspaces. Right? So let us decompose V, which is say R3, into two subspaces. Say V1 is the xy plane and V2 to be say the z axis. Right? So the projection of any vector onto V1 is perhaps the following. Right, 1 1 0 0. Okay. So firstly note that V is a direct sum of V1 and V2. So this corresponds to V1, and what is the projection onto the z-axis? It is 0 0 0 0 0 0 1. Right? So clearly, so this is my E1 and this is my E2. So clearly E1 E2 is equal to the 0 matrix, and E1 plus E2 is equal to the identity. Right? So in fact, this holds not just for this particular example that I've given, but you can construct other examples as well. So for example, try to take an arbitrary plane, right, and try to find, so call this V1. So take any plane in R2, take this as V1, then take V2 as so take V2 to be some other line which is not in R2, right, and try to find the corresponding E1 and E2, and you should verify that E1 E2 equal to 0 and E1 plus E2 is equal to the identity matrix. Right?